Okay, hello everyone. Welcome to our weekly seminar at Jagiellonian. The speaker today is David Wood, who works at Monash University in Melbourne. So, well, at least from my perspective, David is an expert in structural graph theory. He for sure enjoys various types of graph colorings. He can be obsessed with graph layouts. He's truly active member of our research community, and I can tell you he cares about good math, he cares about good writing, good use of English. So today I'm a little bit scared because of the infinite graph setup. But still, David, thank you for joining us today. And the floor is yours.
Thank you, Patrick. It's an honor to speak in your seminar today. Don't worry, I'm just equally scared about infinite graphs. This is the first paper I've ever written on anything infinite. But I can assure you that most of the mathematics is really done in the finite case. And then you just have to push a little bit further to get to the infinite. All I'm talking about today is joint work with Tony Hun and Boya Moha, Robert Samal and Carsten Thomason, although nearly all the work really builds on previous papers with several other authors who I'll mention along the way. Let me start with this general picture of minor closed graph classes. So at the bottom of the picture, we have simple class of forests, which are examples of planar graphs, which are examples of graphs of bounded genus, which meaning you can just be embedded on a fixed surface. And all these are examples of minor closed classes. So here, a minor is a graph obtained from another graph by vertex or edge deletion plus or edge and edge contraction, which means to take this red edge in the picture, delete the red edge and identify the two vertices and replace any parallel edges by single edges. So this is examples of minor closed classes. Now, one of the most useful types of theorems in structural graph theory is a theorem that describes a complicated class of graphs in terms of some simpler class and then some operations. And the classical example of this type of theorem is the graph minor structure theorem of Robertson and Seymour. And what they were able to show is that every minor closed graph class can be described in terms of simpler classes, where the simpler classes are graphs of bounded genus and planar graphs, plus some other operations, including apex vertices, something called vortices that I won't describe, and the clique sum operation. So all these, any minor closed class can be described from these sort of basic building blocks. But a question that has bothered me for quite a long time is, what is the structure of planar graphs? Can we describe planar graphs in terms of some simpler building block? And the graph minor structure theorem just doesn't answer this question, because planar graphs are the simplest of all the building blocks in the graph minor structure theorem. So the short story is that we answer this question using something called product structure. And what we're able to do is describe any planar graph in terms of graphs of bounded tree width. I'll define what that means later on. But I think it's fair to say graphs of bounded tree width definitely are a simpler class than planar graphs. For example, if you take most NP-complete problems become polynomial time solvable on graphs of bounded tree width, but typically speaking, they stay hard on planar graphs. So that's one reason why I put this dotted barrier between the hard and easy classes between planar and bounded tree width. But another good reason is that if you go from, well, I claim that planar graphs are really the first class of graphs on the hard side of the hard line. Because if you take a minor closed class, and all you have to do is exclude one planar graph from that class, then the theorem of Robertson and Seymour says that that class drops below the easy, over the line into the easy class, because it becomes a class with bounded tree width. So really planar graphs are the the first hard class in this picture. And really, if you understand planar graphs, often using the tools of graph minor theory, you can make interesting conclusions about graphs of bounded genus and more generally minor closed graph classes. So planar graphs are critical to understand their global structure. And indeed, I should mention that graphs of bounded treewidth, there's no surprise that they appear here, because indeed they're implicit in the graph minor structure theorem of Robertson-Seymour. And Robertson-Seymour even invented the idea of a tree decomposition, which defines them. But not only do we get product structure for planar graphs, we also get product structure for graphs of bounded genus, and in fact, any minor closed graph class. So we really are saying a new version of the graph minor structure theorem using graph products. The other nice thing about these product structure theorems is that they actually apply beyond this picture, and we can describe certain non-minor closed graph classes using product structure as well. The new thing that I'd like to talk about today is the notion of a universal graph, which also arises from this product structure theorems. So I encourage you to try and keep that picture in the back of your head. It helps to think of these broad pictures when looking at the more detailed results to come. Okay, what's a universal graph? Well, suppose we have a graph class script G. We say a graph U is universal for a graph class script G if U is in the class and U contains every graph in the class. Now, if I say contains, it means as a subgraph. But now think about this.
Excuse me, do you mean induced subgraph or just okay.
Subgraph. I will talk about induced subgraphs in the second half of the talk, but I'll say induced then.
Okay.
For me, a subgraph is not necessarily induced.
Okay, I got it. Thanks.
Now, so take this, imagine that this graph class script G is an infinite class. Most classes that are interesting are infinite. They have unbounded size finite graphs. But if this graph U contains every graph in the class, then U has to be infinite. So this U will be infinite. But what's stopping me simply taking the disjoint union of all the graphs in the class? If this graph class are finite graphs, then I can just take a disjoint union of all the graphs, and that's a universal graph. But that's not at all interesting. So the way to avoid this issue is to actually assume that all the graphs in here are also infinite. Right? So this class G is actually a class of infinite graphs. And then this question of does a class have a universal graph? Then it becomes interesting. Now I'm going to assume that all my graphs are countable. So the size of the vertex set is finite or is a countable set. Now you can't ask these questions for uncountable graphs, but I don't want to go there. And if Piotrek is scared of infinite graphs, then he definitely will be scared of uncountable graphs, and I'm absolutely afraid of them. So let's not go there. Certain technicalities arise that are best avoided. Okay, hopefully you understand the definition, but if not, here's a very simple example which highlights that this really isn't so scary. I claim that there is a universal graph for the class of trees. And here it is, I've defined it explicitly. The vertex set of this graph at the moment is the vectors x1 to xn. N is any natural number, and x1 to xn are any natural numbers. And then the edges of this form, x1 to xn, is adjacent to x1 to xn plus any other term here. Now, if you think of this as a vertex, and you just delete the last entry, then this is the parent. So this defines a tree. And there it is, I've drawn it. Here's the root, where n is 0. Vertex 1, 2, 2 has got children, but its parent will be 1, 2, obtained by deleting the last entry in that vector. Now this is an infinite tree. Every vertex has infinite degree, but it's a countable tree. It's a countable union of countable sets. So it has countably many vertices. But the important thing for me, is that it contains every tree as a subgraph. Indeed, it contains every forest. So this is a universal graph for the class of forests, you could say. Yeah, I give this example to show you that you really can construct very explicit, concrete examples of universal graphs. Please interrupt if you've got questions. Okay, now Stanislaw Ulam asked a very good question, roughly 60 years ago, I'm guessing. He said, is there a universal planar graph? So is there an countably infinite planar graph that contains as a subgraph every countably infinite planar graph? It's a really good question. And Janos Park answered this question in one of Janos's very first papers, hence the very young photograph of Janos Park. And he proved the answer is no to Ulam's question. He showed that there is no universal planar graph. It's a beautiful proof, quite a short, elegant argument, a good one to read. Now let's sort of restate Park's theorem in light of Kuratowski's theorem. So Kuratowski says a graph is planar if and only if it has no subdivision of K5 or K33. So what that says then is that if a graph U contains every planar graph, well, then we know it's not planar. So in fact, U must contain a subdivision of K5 or K33, as illustrated in the pictures. Now, if you see the theorem stated this way, and you see the conclusion is a K5 or a K33, it's natural to ask, well, can we strengthen the conclusion of this theorem? Can we replace K5 by something bigger? And the answer is yes. And I call this the bad news theorem. We proved that if U contains every planar graph, then not only does U contain K5, but it has to contain every complete graph, every finite complete graph, I should say. And more than that, for every integer n, this graph U must contain a subdivision of the complete graph on n vertices and with multiplicity n. So every edge appears n times in this subdivision. So that's the bad news theorem. Okay, let's state Park's theorem in light of the Wagner's version of Kuratowski's theorem. And now we replace subdivision by minors. So the theorem becomes, if U contains every planar graph, then K5 or K33 is a minor of U, meaning I can contract these connected balls here to get a K5 or a K33. Okay, we do the same thing as before. Can we strengthen the conclusion? And the answer is yes. I call this the really bad news theorem, because we prove that if U contains every planar graph, not only does it contain K5 as a minor, but it contains an infinite complete graph as a minor. So this is the really bad news. So the answer to Ulam's question is no, 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 in a very strong sense. And, not only is there no universal planar graph, but every graph that contains all the planar graphs, in fact, must have an infinite complete graph minor. So that's our bad news theorem. Let me give a quick sketch of this. Actually, I'm going to skip my sketch and go on to the next question. I don't want to spend time on that. Okay, so let's revisit Ulam's question. So Ulam asked originally, is there a universal planar graph? Now, I would like to rephrase that in light of these negative results and ask, well, what is the simplest graph that contains every planar graph? We know that this simple graph can't be planar. In fact, it must contain an infinite complete graph as a minor. But can we still get a graph that's simple in some sense and it contains every planar graph? So what would be the desirable properties of this simple graph? Well, surely you'd want it to have bounded chromatic number, because planar graphs are four-colorable. You'd want that this pseudo-universal graph to also be four-colorable, or at least have bounded chromatic number. Well, what else? Well, an important structural property of planar graphs is that they are 5 degenerate. So here a graph is D-degenerate if every finite subgraph has minimum degree at most D. It's important that you add the word finite here, because otherwise, like the infinite tree with infinite degree at every vertex would not be one degenerate, and you want every tree to be one degenerate. So planar graphs are 5 degenerate, so you'd want that your simple graph that contains all the planar graphs to have bounded degeneracy, preferably 5. Well, what other properties would you want of your pseudo-universal graph? Well, the key property of planar graphs is that they have balanced separators of size √n. This is the Lipton-Tarjan separator theorem. So we'd want that every finite n-vertex subgraph of our pseudo-universal graph to have order √n balanced separator. Now, if you know anything about sparsity theory of Nesetril and Osona de Mendes, you'd probably say you'd want that this pseudo-universal graph to have bounded expansion. And that would be a key property in the light of sparsity theory. So what does this bounded expansion mean? Well, Nesetril and Osona de Mendes defined this function here, nabla sub R of a graph, to be the supremum taken over all the finite R shallow minors of G of the average degree of this minor H. And R shallow means that when we contract balls to go from G down to H, we only contract balls of radius at most R. That turns out to be a very good definition. Then Nesetril and Osona de Mendes would define a graph class to have bounded expansion. If taken over all the graphs in the class, this nabla sub R function is bounded by a function of R. In the case of infinite graphs, you can actually simplify this definition, because you can just say that nabla sub R of G is at most f of R, because there's already infinitely many finite subgraphs of G in that case. Anyway, we definitely would want to have bounded expansion in our pseudo-universal graph. I should say that if this function f of R down here is independent of R, it's an absolute constant, then that would mean that this class actually excludes a fixed finite minor. But we've shown that that's impossible. So definitely this f of R function will be increasing with R in our pseudo-universal graph. And finally, a possible desirable property is that this simple graph contains no subdivision of the infinite complete graph. Now, if you think back to the bad news theorem, we didn't exclude this, so this is possible. All right, so let's think about what would probably be the first guess at a graph that contains all the planar graphs. Perhaps your first guess would be the complete four-partite graph with infinitely many vertices in each color class. Now, that does contain every planar graph. Every finite planar graph is four-colorable by the four-color theorem, and then by the Erdős-de Bruijn theorem, that says that every planar graph is four-colorable. So this complete four-partite graph definitely contains every planar graph. It obviously satisfies one, but it fails all the other properties. It has unbounded degeneracy, definitely no separators, no bounded expansion, and it contains it definitely contains a subdivision of an infinite complete graph. So it fails most of our properties, so that's no good for us. Well, what else might we do? Well, there are results focusing on the second property. For every number D, there's a universal D-degenerate graph. So this graph with D equals 5 contains every planar graph, and it satisfies 1 and 2. This graph would be 6-colorable, but it fails properties 3, 4, and 5. So that's not so good for us. But the good news theorem is that there exists a graph that satisfies properties 1, 2, 3, and 4, so that's most of ours, and there's another graph that satisfies 1, 2, 4, and 5. So that's another useful graph. It satisfies most of our desirable properties, and each of these graphs still contain every planar graph as a subgraph. Just to see where we're headed, the first graph will be described by a product structure, and the second graph will be described using a tool called chordal partitions that I'll talk about later on. So in the remainder of the talk, I'm going to focus on these two graphs and describe the constructions of these two graphs and give you a hint about why they work. Okay, to talk about the first construction, I need the standard definitions of graph products. Here on the left is the Cartesian product. If you think of it as take this first graph as the red graph, then each row will be a copy of the red graph. And then if the second graph is the blue, then each column is a copy of the blue graph. So that defines a Cartesian product. Then the direct product, sorry, the one in the middle, has got all the cross edges, but none of the edges inside the rows and columns. And then the strong product on the right is the union of the Cartesian and the direct product. So for every edge if I take this edge and this edge, then you look at the corresponding 4 vertices in the product, and they will form a K4. That's which matches pick the notation here. So I'll be talking mainly about strong products. But before I jump to strong products, there's a useful property of the direct product. And the property of the direct product is that the direct product of two graphs is colorable by K colors, where K is the minimum of the chromatic numbers of the two graphs in the product. So this is the obvious upper bound on the chromatic number of a direct product. So this has a useful corollary for universal graphs, because suppose you have any graph U and it contains every planar graph. Then I claim that if you take the direct product of U and just K4, then that contains every planar graph still, and it's now 4 colorable. Because if you give me a planar graph G and then I know it's 4 colorable, I can use that 4 coloring to map the vertices of G into this product U times K4. But U times K4 is still 4 colorable because the chromatic number of a direct product B is at most the minimum of the chromatic numbers of A and B. So this is an easy way to get a graph that satisfies desirable property 1, because that was 4 colorability. Now you can easily do this just with the direct product. So property 1 is actually very easy to achieve. Now the other ingredient that I'll need to describe these constructions is that, go ahead.
So in the previous example, oh, never mind. It's already answered my question. Sorry.
That's all right. I'm glad to take questions.
I was wondering. Oh, never mind.
You sure? Sounds like you got a good question.
No. I was just surprised to see a triangle in this direct product, but it makes sense if we take a product with something that contains a triangle.
Yes, if you take this P3 to be more than a path, then yeah, you'll get it. Yep. Oh yes, the other ingredient I need is tree width, which I mentioned earlier. So tree decomposition of a graph represents each vertex as a subtree of a tree, so that subtrees of adjacent vertices intersect in G. So here's a graph G, and vertex B here is represented by this subtree marked in B, and vertex E is represented by this subtree marked E. And while BE is an edge, so those two vertices have to appear at a common node in the tree. We call this set of vertices here a bag. So that's a tree decomposition. The width of a tree decomposition is the maximum size of a bag minus 1. So in this example, the width is 2. Then the tree width of a graph, denoted TW of G, is the minimum width taken over all possible tree decompositions of G. So tree width is the standard measure in graph structure theory of how similar a graph is to a tree. Indeed, a graph has tree width the most 1 if and only if the graph is a forest. Now, it's folklore that there is a universal tree width k graph for any given integer k. So I'd like to describe an explicit construction, which I think is quite a cute construction. And it turns out that it's useful for other things. So let's describe this. So suppose you have a tree, which is the tree in blue in the picture, and the edges are oriented with in degree at most 1 at each vertex. So you think that an edge is oriented from its parent down to the child. And now I assume that the vertices are properly colored as well. And now, given this colored tree, I'm going to define a graph, call it T plus, and the vertex set of T plus is just the vertices of the tree, but then I add extra edges. So when do I add the edge VW into this graph T plus? Well, I add the edge VW if W is an ancestor of V, and V and W have different colors in the original coloring of the tree, and finally that no internal vertex on the WV path is colored W. So let's see what this means in practice. Say here's V, and I imagine this is the W1. Well, W1 is an ancestor of V. They have different colors. One's red, one's green. And there's no internal vertex on the WV path. So W1V is definitely an edge in T plus. In fact, every edge of the tree is an edge of T plus. But what about this W2 up here? Well, it's green. And by the second property here, I don't add edges between two green vertices. So W2 is not adjacent to V. What about W3, this yellow vertex? W3 is an ancestor of V in the tree. They have different colors, and no internal vertex on the VW3 path is colored yellow. So that means I do add the edge VW3 into T plus. So that defines T plus. And now imagine if you take T to be the universal tree, which we saw at the start, color it so that with K plus 1 colors, such that each vertex has infinitely many children of each color, which definitely can be done because each vertex has infinitely many children, and K is finite. And from that coloring of the universal tree, I take the graph T plus, and let's call that T sub K. That's just a single graph. And the theorem is that TK is a universal tree with K graph. So it has tree with K, and every tree with K graph is a subgraph of TK. That in itself isn't so startling, but it turns out that using this explicit construction, we can prove a number of other stronger properties that are very useful in the other theorems to come. So it helps to have a very concrete description of this universal tree with K graph. Some other useful notions from the theory of tree decompositions is of adhesion. In this picture here, the yellow set is a bag, the green set is a bag. Each of these are bags. And we define the adhesion of a tree decomposition to be K if the intersection of any two adjacent bags has got size at most K. And then we define the torso of this node X to be the graph obtained by the subgraph induced by the vertices in the bag, plus by adding a clique on the intersection with any adjacent bags. So that defines the torso of the bag. Now, if we define D of G to be the graphs that have a tree decomposition in which every torso is a subgraph of G, then, well, we can actually prove that this class has a universal graph. And I'm going to denote that by this G hat operator. So, for example, this implies is stronger than the tree with K universal graph. Because if you just take G to be the complete graph on K plus 1 vertices, then this G hat is the universal tree with K graph. So this is a strengthening of the fact that we have a universal tree with K graph, and the proof of this builds on that explicit construction of a tree with K graph that I mentioned in the previous slide. And we can also add adhesion into the picture. If you define TK of G to be the graphs that have a tree decomposition which every torso is a subgraph of G, and you have the adhesion at most K property, then still we have a universal graph for that class. So that's useful and later on in the talk. Okay, so finally I get to probably the star of the show, which is this theorem that we proved a few years ago with Vida Dojmovic, Gwenaël Giray, Piotr Micek, Pat Marin, and Torsten Eckhart. And we showed that every finite planar graph is a subgraph of some strong product of graphs H and P, where P is a path and H has got tree width at most 8. Now, it does take a while to digest this theorem. So you give me your favorite finite planar graph, then I can construct a graph H with tree width at most 8, and I take a long enough path, and I consider this strong product, which is shown here, and magically, somewhere in here is the graph G as a subgraph. This is a surprising and very useful theorem. It's had a lot of applications, and just in a couple of years, it's been used to solve a number of outstanding open problems regarding Q layouts, non-repetitive colorings, P-centered colorings, adjacency labelings, and others. And there are other papers that will be appearing soon with more applications of this theorem. There's a variant of the theorem which was proved by the same authors, where we added sort of a third dimension to the product, and it's bounded tree width times a path times a triangle, but the bonus here is that we get the tree width bound down to 3 instead of being 8. There was a follow-up paper by Torsten Eckhart, Wendy Yee, and myself, where we improved the upper bound from 8 to 6, and we also showed that you can do it with something called simple tree width, which I won't go into. It says it suggests a slight strengthening of the notion of tree width. And this theorem down the bottom here also has simple tree width. In fact, in all these theorems, the graph H is planar, as well as having bounded tree width, because H will be a minor of G. Okay, let me tell you why this theorem is so useful, and let me illustrate it by talking about non-repetitive colorings, which certainly is a topic that's very popular in Poland. So what's non-repetitive colorings? I feel like I'm preaching to the converted here. To describe what's a non-repetitive coloring, first of all, we have to know what's a repetitive coloring. And so a coloring of a path is repetitive if the sequence of colors on the first half of the path is the same as the sequence of colors on the second half of the path. Now, what I care about is colorings of graphs in which no subpath is repetitively colored. So if you look at this 8 cycle on the right here, you can take any subpath. I claim that it's non-repetitively colored. Like if I take this 4-vertex subpath, the colors are blue, red, yellow, red. That's non-repetitive. But I can also take 6-vertex subpaths, and I get yellow, red, blue, yellow, red, yellow, and that's also non-repetitive. And you can check. Every subpath of the cycle is non-repetitively colored. Now the origins of this, before I get to the origins, the definition that we care about is pi of G is the minimum number of colors in a non-repetitive coloring of G. Now the origins are Thury's theorem from 1906, which says that paths are non-repetitively 3-colorable. Now it should, if you haven't seen this before, it should strike you as an amazing theorem, because these paths are arbitrarily long, and you have to exclude repetitively colored subpaths of any length. But Thury proved this in this beautiful way. He showed that if you start with any non-repetitively colored path and simply replace each orange vertex by that subpath, so this orange one gets replaced by the same subpath, and the blue ones get this subpath, and the green ones get replaced by that, and you just blow up the path in this fashion. And if the starting path was non-repetitive, then the new one is non-repetitive as well. So that shows that arbitrarily long paths are non-repetitively 3-colorable. Now, Thury wasn't interested in coloring graphs. He was interested in words. So this theorem is actually described in terms of a word over an alphabet of 3 characters. It was a paper of Alon, Grichuk, Haluchak, and Riordan, which generalized this idea to graphs. And in the first paper on the topic, they showed that graphs of max degree delta are colorable with big O of delta squared colors. It's a beautiful example of using the Lovász-Lókő lemma. But in this original paper, they left with the following open problem: is do planar graphs have bounded pi? I really like this problem because somehow I feel like it's a marriage of 2 fundamental topics in combinatorics. On one hand, you've got planar graphs and the 4-color theorem and coloring planar graphs. And on the other hand, you've got the entire field of combinatorics of words and the foundational result of TUI, and you put them together and you get this question: do planar graphs have bounded pi? And this was considered the most important problem in the field. Nearly every paper on the topic in these 20 years since then have asked this question. And really the answer is yes. And it's a very simple corollary of the planar graph product structure theorem. And so here's how you prove it. So the planar graph product structure theorem describes planar graphs in terms of bounded tree width graphs. So first of all, the first ingredient is you need to know whether bounded tree width graphs can be non-repetitively colored. And Kundin and Pulsmeyer did that for us. They showed that the non-repetitive chromatic number is at most 4 to the power of the tree width of your graph. And then we defined something called strongly non-repetitive, and I'm not going to say what it is because you don't really need to know, but it's a slight strengthening of non-repetitiveness. Why did we define this? Well, we defined it so that we could prove a lemma about products. And this is the lemma that we needed. We showed that the non-repetitive chromatic number of H times a path is at most 4 times the non-repetitive chromatic number of H. So you needed strongly here because you need strong on both sides of this inequality. That's just a technicality, but it still is an important definition to come up with the right notion of strong non-repetitive coloring. Then we took the proof of Kundin and Pulsmeyer, and I observed that exactly their proof actually shows the stronger statement with the stronger non-repetitive property. And now you can just plug all these things together and you get a theorem for planar graphs. Take any planar graph G, pi of G is at most pi star of G because it's stronger. G is a subgraph of H times P, where H has got true at the most 8 and non-repetitive colorings are closed under subgraphs. Then we apply the first lemma to the product and we get this inequality. Then we apply the second lemma because H has got true at the most 8, and we get that the planar graph is non-repetitively colorable with 262,000 colors. This was done in a paper with Vita Domovic, Louis Esperet, Gueniel Giray, Bartosz Rolczak, myself. Now you might think 262,000 colors is too many. Well, if you use the other version of the planar graph product structure theorem, because here you've got tree width 3 and the dependence on the tree width is exponential, you do the calculation again and you end up with only 768 colors. And that's solves the problem on non-repetitive coloring of planar graphs. All right, let's get back to the infinite graphs. So we know the planar graph product structure theorem for finite graphs, and then we have the following compactness step, which says that if tk, that's our universal tree width k graph, times p here, script p is a one-way infinite path, and then KC is just a bounded sized complete graph. If that contains every finite subgraph of some infinite graph G, then in fact this graph contains G itself. This is the standard sort of argument that you use to extend results for finite structures to infinite structures. The proof of this actually took us quite a long time to find. And the key was to actually translate the product into something called layered partitions, which is an equivalent set of words to describe the same thing. And once you think about it in terms of layered partitions, then the proof is straightforward. And you can use Koenig's lemma, which is a key tool from infinite combinatorics, to conclude this compaction step. So then we can put this all together and we get out.
The TK is this explicit construction for the universal graph of treewidth-k, right?
Exactly. This is the universal treewidth-k graph. You could put other graphs into this lemma. This lemma, this compactness lemma, doesn't really need. Oh no, it doesn't. No, I shouldn't jump ahead. No, let's just keep that lemma as is. I don't want to generalize it on the fly. Okay, so we put all this together and we get our first examples of graphs that contain every planar graph. We get that T6 times P contains every planar graph. T6, remember, is the universal treewidth-6 graph times a one-way infinite path. And then we also get the universal treewidth-3 graph times a one-way infinite path times a triangle. This also contains every planar graph. So let's think, is this theorem any good? Does it satisfy the desirable properties that we had at the start? Well, you can easily show that. Let's just think about the first one. It is 14 colorable. That's an easy argument. It's 19 degenerate. So every finite subgraph has a vertex of degree at most 19. Again, that's not easy, not hard to check. You can also check that every n-vertex subgraph has got tree width order root n, which implies you have a balanced separator of size root n, which means that the finite subgraphs of this T6 times P can satisfies Lipton-Tarjan's theorem, which is a strong property. We have something called strong coloring numbers bounded. I'm not going to define this, but this is a key property in the sparsity theory. And in fact, the strong coloring numbers are even linear in R, which is a very strong property. And this implies bounded expansion, and indeed it implies linear expansion. So the expansion function is even linear in R. So this graph satisfies 4 of the 5 desirable properties in quite a strong sense. Let me mention just a little open problem here, is can you delete this K3? I'd love to be able to do that, but we have no idea how to do that. It's a very nice question. Okay, so that's the product structure for planar graphs. So these results are quite robust in that they quickly generalize for broader classes. You can go to graphs embeddable on any fixed surface, take a surface of Euler genus G, and you take the class of all graphs that can be embedded on that surface. Then these graphs contain every such graph that can be embedded on the surface. And they all have the same structure as before, but just slightly complicated, more complicated. This part is bounded tree width times a path, where the bound now depends on the surface. But the tree width only increases linearly with the genus. So, and this graph has all the properties that you'd want. And you can generalize this to many non-minor closed classes. For example, you can allow a bounded number of crossings on each edge, and still you're able to conclude product structure theorems for such classes where the tree width of the graph H now depends on the number of crossings that you allow on each edge. Something called map graphs and other examples of non-minor closed classes can be proved to have this product structure theorems. And in fact, we prove this. This is joint work of Vita Dorovich and Pat Marin, all in a unified way, something called shortcut systems. I'm not going to go into that. Okay, finally I get to minor closed classes, a general minor closed class. So what is the product structure now for a general minor closed class? Well, here's the theorem we're able to prove. It says take any proper minor closed class, that there exists constants K and A, such that every finite graph in the class is a tree decomposition in which every torso is isomorphic to a subgraph here's the new part and the important part. So every torso is basically contained in the product of a bounded tree width graph, because H will have tree width K, and a path P. That's the same structure as before, but now we add this new part, which is a complete join with a bounded size complete graph. So this operator means complete join. So this just means add A vertices and make it adjacent to everybody. So these are the apex vertices from the graph minor structure theorem. This theorem is proved using the graph minor structure theorem, but it turns out that this statement is a very useful, and I find it easier to apply than the original graph minor structure theorem, because the original graph minor structure theorem has these things called vortices, and then you need to do some topology in there, and you need to deal with clique sums. But this theorem at least eliminates the vortices and all the topology, and all you have to deal with are these very nicely structured graphs of the form bounded tree width times a path, complete join to a bounded set of apices. And you can see that this is useful, and it's an easier approach than applying the graph minor structure theorem. And here's two papers that have used this approach. One was with Chun-Hung Liu, where we looked at something called cluster coloring. And then there's a very recent paper which solves deep problems from geometric, what am I saying? Metric spaces, sorry. And they use a very similar version of the graph minor structure theorem here, where they, instead of the products, they have something called layered tree width. But still, it's very helpful to avoid using having vortices in the graph minor structure theorem. So we can put this together for infinite graphs now, and we get probably the main theorem of the talk, which says that for every minor closed class G, there exists numbers K and A, and there is a single graph U, just one graph, and it contains every graph in this minor closed class. So what is the graph? Well, I take the universal tree width K graph, times it by a path, add my bounded number of apices, and then I take this hat operator, which enables me to take tree decompositions. But it is a single graph. It contains every graph in the class. You can check it will have bounded degeneracy. It will also have root n separators. We'll still have linear coloring numbers and linear expansion. It has an extra property called low tree width coloring, which says that for any integer c at least 2, you can color the vertices with c colors, and the union of any c-1 color classes will have bounded tree width. So it was known that minor closed classes have such colorings. This was proved by De Vos et al. But it's interesting that this universal graph U actually has the same property. Okay, so that's property, everything I want to say about products, and I've gone much slower than I planned. So let me just say the final theorem, and I won't say anything about the proof. So recall from the beginning of the talk that if some graph U, remember this is an infinite graph, contains every planar graph, then it must be that U contains a subdivision of a finite complete graph Kn for every finite number n. And it also has to contain an infinite complete graph as a minor. So the natural question is, can you strengthen this theorem to say that it must contain an infinite complete subdivision? And when we first thought of this question, we said, well, surely the answer is yes. Not that much difference between minors and subdivisions. Surely we can strengthen it to subdivisions. But it turns out the answer is no, because we actually constructed a graph that contains every planar graph, and it contains no infinite complete graph subdivision. So it must have an infinite complete graph minor, but in fact it can avoid infinite complete graph subdivisions. It also has many of the previous properties. It's 21 degenerate. It has linear expansion still, and that implies bounded expansion. But the bonus and the strengthening, and to answer the question from the beginning of the talk, is that this graph has a stronger property, is that it contains every planar graph as an induced subgraph. That's much stronger. And then we can strengthen it further because there's really nothing special about planar at all. We can replace planar by KT minor free, and still we have the theorem. And so it now says for every T, there exists a graph that contains every KT minor free graph as an induced subgraph. It avoids infinite complete graph subdivisions. It's big O of T squared degenerate, and it has a linear expansion in R, and the constant that depends on T is only T squared. And there is no hidden constants here. The previous theorem had Robertson-Seymour hidden constants, like towers of 2, and here the constants are all very reasonable because the proof avoids the Robertson-Seymour graph minor structure theorem entirely. The proof uses something called chordal partitions. Do you want to hear this, Piotr, or should I?
What is the property that you lose comparing with the previous theorem?
Yes, excellent question. So the construction based on products had big O of root n separators. That's not on my list, but this graph actually does have n to the 3/4 polylog n separators for n vertex subgraphs. So it's not that bad. It still is strongly sublinear separators. This uses the Plotkin-Rao-Smith paper, if you know that one.
Thanks.
Now, yeah, so I'm short of time, so I don't want to say much about the proof, except to say that it uses something called chordal partitions, which is one of my favorite topics. Chordal partitions are incredibly useful definition, essentially, and it's been used for all sorts of things. It was originally used by Andre, then rediscovered by Reed and Seymour in their paper on fractional coloring. That's where I learned about it, and it's been used by lots of people ever since. And it's a very important tool. If you ever want to study a minor closed class, and you care about the dependence on the excluded minor, then look at chordal partitions, because you avoid all the big constants that come from Robertson-Seymour graph minor structure theory. All right, so I'm going to skip a little bit of proof here and say we can use chordal partitions for a bunch of other things. For example, we get a universal graph for treewidth-k graphs as induced subgraphs, because chordal partitions work with induced subgraphs. So that's neat. We actually get the following curious theorem. It says there exists a single graph. It has no complete graph as a subdivision, an infinite complete graph subdivision, but it contains every locally finite graph as an induced subgraph. So locally finite means that every vertex has got finite degree. That's a curious theorem. And it's just an explicit construction, no hidden magic. Okay, let me finish and wrap up. Let's go back to the original question. What is the simplest graph that contains every planar graph? And we identified these properties here, 1, 2, 3, 4, 5, and I showed you that the construction based on products satisfies properties 1, 2, 3, and 4, and the chordal partitions construction satisfies 1, 2, 4, and 5. So the natural question is, well, can you do them all? Can you get a construction that satisfies 1, 2, 3, 4, and 5? And really, you can add your own favorite properties. Don't take it from me that these are the best properties. They're just my opinion. Maybe you've got other properties that you should look for in your universal graph. Another open problem is whether this linear term in the expansion can be improved to little o of r. I think that's quite a hard question. I have no idea. What about universal graphs for border classes of graphs? What about if your input class is the classes with linear expansion? Can you get a universal graph for that class? Don't know. But what if you replace linear by polynomial expansion? Is there a universal graph for that class? Again, I have no idea, but I think these are interesting questions. So really, I think of universal graphs as like the ultimate structure theorems, because you've got a single graph and it contains every graph in your class. So this is very much, these questions are about finding the structure of sparse graph classes. And I think universal graphs are a very nice way to formulate the question of what is the structure of a sparse graph class. Okay, with that, I'll stop and thank you very much for your attention.
Thanks.